So this is the technique or approach we're going to use to find those partial fractions. 1, we need to check that the degree of the numerator is less than the degree of the denominator. It has to be. If it's not, then we will use polynomial long division, which I warned you was going to rear its head in this section. So we'll use polynomial long division to rewrite that integral if it's not. Oh, just highlight the whole thing, right? So you definitely need the degree of the numerator to be less than the degree of the denominator. That's key. That's probably the most important bit on that. Then you're going to factor your denominator as completely as possible. That'll actually often be done for you, but nevertheless, and you need it to be irreducible factors. They have to be factored completely. Then you're going to rewrite your integrand using partial fractions with unknown coefficients. So you're going to split it up. So if you have linear factors, which is ax plus b to some power, you'll write a constant, capital A, over that linear factor plus another constant. And they're using A1, A2, that's fine. You can use A, B, C, or you can use A1, A2, A3. It'll all work. If it's powers of x, x is technically a linear factor. This is like a special case of this one above. So it'd just be A1 over x, A2 over x squared, and so on. This actually is the same example as up above. And then quadratic factors, you actually top them with linear factors. So if it's ax squared plus bx plus c, you have a bx plus c above it, right? And then another one, and then another one. And you keep going until you reach the highest power you have. It is possible to have combinations of those cases. That definitely will happen. Let me think. If the denominator of the rational expression has a repeating linear factor and a separate quadratic factor, for example. And it's going to take time and patience. This is going to be tedious. But it's not calculus, actually. What you're doing is a pre-calculus algebra type thing. It's just that we don't teach it often in pre-calculus and algebra because they don't have any need for it, but you do. The powers of x case, I already said that. Case number 2 is actually just a special case of case number 1. More complicated partial fractions decomposition may require the use of matrix algebra for solving multiple linear equations at once. We won't do that really in this particular class, but that is possible if you keep going on. You could have, cubics and things like that, and then you may want to deal with it in terms of matrices. All right, so that's the breakdowns of the cases. So you're going to rewrite your integrand as partial fractions with unknown coefficients, and then you'll find an equation that relates the unknown coefficients. You'll solve for the unknown coefficients by substituting different values, and there's 2 separate methods: substituting of variable values and solving for the constants, or creating a large polynomial and solving for constants. Then you'll rewrite the integrand as a sum of partial fractions and find the integral. All right, seems straightforward enough, right? Okay. Well, let's see it in practice, because the method doesn't really mean much unless we actually use it. Okay, so we're going to look at the one that we actually know the answer to because it was on a previous page, but we're going to look at it. Okay, so step number 1, and method number 1, we're going to substitute variable values and solve for the constants. Don't worry about that yet. I'll explain it as I go. All right, so step number 1, 3x plus 11 over x squared minus x minus 6. So the degree of the numerator is less than the degree of the denominator. So right, yay. Maybe we can make a little comment. Okay. So step number 1, actually I'll just put it this way. The degree of the numerator is less than the degree of the denominator. Check. You usually put that somewhere, right? Actually, I could even do it up here because it's the step number 1 for both of them. You just kind of have to check it. The degree of the numerator is 1, the degree of the denominator is 2, and so we're good. That saves me room down here for what I'm going to need to do. All right, so that would be equal to, now step number 2, right, so step number 1's done. Step number 2, I'm going to factor, which I already did on the previous page, so I'll do it again. 3x plus 11 over x minus 3, x plus 2. Okay, now step number 3. We need to rewrite it in one of these cases. So we look at our denominator factors, and they're both linear factors. It's x minus 3 and x plus 2. So we're going to have a over x minus 3 plus And we could use A1 and A2, or we can use A and B. I usually just do A and B unless I have a reason to number them. So I'm going to say A over x minus 3 plus B over x plus 2. I'm leaving myself a little space because I need to do something in a minute. Okay, so there's step 3 right there. I just wrote it. All right, step 4. Find an equation that relates the unknown coefficients. So the equation will be, if I multiply everything by x plus 2 over x plus 2 and x minus 3 over x minus 3. In other words, here, let me do it this way. If I multiply everything by the common denominator, x minus 3, x plus 2. If I do that, over here on the left, everything will cancel. And I'll be left with 3x plus 11. And that's it, which is good. That's what I wanted. Over here, I will have a. The x minus 3's would cancel, and I'd be left with x plus 2. Plus, and for b, the x plus 2's would cancel, and I'd be left with x minus 3. There's step 4 right there. I have an equation that relates the unknown coefficients with, well, known coefficients. Now, here's where the methods change, and this is where the divergence happens. So for step 5, what we want to do is we want to, for this method, we're going to substitute values and solve for constants. So we're going to pick some values for x, right, for the variable. I'm going to choose -2. I have my reasons. Okay, so if I said, let's say, take this equation. This equation's great. That's my base equation. And I'm going to substitute -2 in there. I would have 5 over here equals a times 0. See why I chose -2. Plus b times -5, right? Because -2 minus 3 is -5. Now, solving that, right? 5 equals -5b. That means that b is -1. I have one of my numerators. Done. And then I'll do it again. I'll let x equal, let me think, what's a smart value to pick? 3, right? Because if I put 3 in, 3 times 3 is 9, 9 plus 11 is 20. A times 5 plus b times 0, this is gone, right? Because 3 take away 3 is 0. And so 5a equals 20, so a is equal to 4. And there we have it. Putting it all together, right? So this was step 5 right here. All of that, step 5. And then step 6, we would rewrite it. So we'd rewrite the integrand. So 3x plus 11 over x minus 3, x plus 2 is equal to 4 over x minus 3 minus 1 over x plus 2. And that we're going to stop right there. We weren't asked to do the integral. We were just asked to find that, so I did. All right, now method number 2 does the same first steps. So it's 3x plus 11 over x squared minus x minus 6. Right, step 1, done. Right, you check that the degree of the numerator is less than the degree of the denominator. Then you factor. Then you rewrite it. All of this is the same. Then you make your equation. Oh, here, just so you can see, it really is the same thing. Ooh, x minus 3, though. I'm making mistakes as I go. All right, so x minus 3, x plus 2. So this becomes x plus 2, and then you'll have x minus 3. So all of that is the same. Step 1, 2, 3, 4. All the same. Where the two methods are different is step 5. So you take this equation and you think to yourself, okay, let's look at some of the terms here. If I distribute this out, let me multiply it out. 3x plus 11 equals ax plus 2a plus bx minus 3b. So I can put together the a and the b. They're terms of x. So they're like terms. And if I look at it over here, they must be equal to 3. So that means that a plus b has to be equal to 3. The three x terms have to be equal to each other. So 3 has to be equal to a plus b, which means that a is equal to 3 take away b. Why do I need that? Well, because then I could look at the constant terms. 11 is 2a minus 3b. So 11 is 2a minus 3b. And then I can take this value for a and I can go substitute it in. And say 11 is 2 times 3 minus b minus 3b. So 11 is 6, take away 2b, take away 3b. So 5 is negative 5b. And sure enough, negative 1 is b. So I get negative 1 is b. And once I know negative 1 is b, then I can go use that back here. Right? I substituted in once, then I'm doing it again. Right? So I used a was equal to 3 minus b. And I substituted it in over here. And then I solved for b. And now I'm taking that value for b and I'm putting it back in. So a is 3 take away negative 1, which is 4. And once I know those two things, and all of that is part 5, then part 6 is just, I would rewrite it. 4 over x minus 3 minus 1 over x plus 2. Oh, and that was my original. I was about to do 3 minus x instead of x minus 3. X minus 3, x plus 2. There's part 6. Just rewriting it. Right? So both methods work. Sometimes one of them is easier than the other. So you kind of use whichever one makes you happy, whichever one you feel like using, and that's fine. So you just use whichever method makes you or feels like it'll work easier for you. And then sometimes you can mix and match them, actually. Sometimes you can do both methods and kind of work your way through it because you'll have so many coefficients to find. And that's it. That's the method of partial fractions. So that's what we'll use. The only thing we haven't done in this example is integrate. That'd be the next step, would be to integrate the problem. But we'll see that in the next example.